Yeah. Good evening, guys. Am I audible? Am I audible? Is it visible? Is the screen visible? I want you people to participate so that I will be able to go ahead. And how many are here? Just to say hi or hello here so that we'll go ahead and continue. I'm just awaiting for your reply so that I will continue because I lost the track of previously what happened in our class. It is, I think we've been discussing about different types of instructions, I guess. Yeah, just I want you people to respond. How many of you people are actually watching so that I'll be able to go ahead? Fine. Yes, okay. Yeah, anyhow, I'm just gonna start. Bigger pardon, my uh, video is not visible. There's a small technical glitch. I'll be able to rectify by the next week. But before that, we just gonna finish what we have, you know, passed in the previous week. Just let us see. If I'm not wrong, I think let me just yeah, in fact, we people are discussing about the memory reference instructions, right? We are in fact you know going through the memory reference instructions. We discussed till end, add, load, store, BSA and BUN, right? In order to just explain you this, anyhow I covered it in the previous week. I will just have a walkthrough these you know memory reference instructions. For this, let me open my PPT. Here now let us discuss about various instructions in terms of the location of the operand. When it comes to the location of the operand, there are three different kinds of instruction formats. One is memory reference instructions, second one is register reference instructions, and the third one is IO instructions. What is memory reference and what is register reference and what is IO instruction? Okay, here when it comes to the memory reference instructions, when it comes to the memory reference instructions, um, all these instructions operands will be available within the main memory. Okay, there are several instructions. End stands for uh, end operation, add stands for add operation, load stands for load operation, store stands for store operation. BUN is branch unconditionally, which is equal to a jump instruction in the high level language program. BSS stands for branch and save the return address. Branch and save the return address. Hi, Lokesh Parab, and you are here, and nobody else. Fine. Lokesh Parab, I do have a doubt, that is, where did I stop exactly in the previous week? Because last week we had a break for Diwali, and that is so I lost the track of what happened previous week. So that I'll be able to go ahead. Okay, from now, from then what I stopped. Where did I exactly stop? Location, there has to be a girl also. Where I exactly stopped? You remember? First of all, am I audible? Yeah, I was explaining. And who else is available right now? Who else is here in the class? What is that girl's name? The location of the operand, not the type of the operand. I'm explaining about the location of the operand. If I'm not wrong, I was discussing about memory reference instructions, register reference instructions, and IO instructions. Yeah, there are 4 people right now, and there is one more girl. There is one more girl who is regular with Lokesh Parab. What is the girl's name? Yeah, fine. Anyhow, I'm just gonna go ahead with these instructions. Here, I was explaining about end. You just yeah, Kirti. Kirti, I don't think Kirti is available right now. If she is there and should have said hi or good evening. Fine. Anyhow, I'm just gonna go ahead with my regular flow of explanation. Yeah. Here we do have, as you can see on the screen, there are 7 memory reference instructions. There are 7 memory reference instructions. I'm going to use my pen here. And add, load, store, BUN, BSE, and ISE. Okay, we discussed already about end, add, load, store. BUN, BSE also. End is end instruction, add is add instruction, load is load. Okay, you know that load, when I say load 450 from the memory location 450, the content will get transferred to accumulator, right? When I say store, from the accumulator to memory location 450, the content will get transferred, right? Yeah. When it comes to BUN is branch unconditionally, which is equal to a jump statement in the high level language. Okay, and BSA is branch and save the return address, branch and save the return address, and which is equal to a call instruction, which is equal to a call to the subroutine. Yeah, am I audible? Am I audible right now? A call instruction to a subroutine. Okay, in fact, I was explaining how when a subroutine is called, how the program counter value will get saved. This is what exactly I was explaining you guys. Okay, I'm gonna close this. Yeah, now is my voice is audible and clear? Good. There is one new guy who's called Mr. Light. Fine. Just better you rename yourself with your proper name so that I'll be able to address you guys. Okay. So here in the last week, I left exactly at this point. When I perform a call instruction, how to save the program counter value. program counter will get saved in stack. Program counter will get saved in stack. That is it. I finished with this. Then ISZ. We will talk about ISZ instruction. Okay. Yeah. Let me explain you guys ISZ. Yeah. What is ISZ? ISZ stands for increment and skip is 0. Increment and skip. Increment and skip if 0. What is this increment and skip is 0 business? How it is going to work? Let us see. Okay. Again, we are going to draw the block diagram of our main memory. This is our good old friend all the time. It just helps us to understand the architecture better and better every time. If you could remember, I've been drawing this memory continuously for giving a complete insight view of the computer architecture, because without main memory there is nothing possible, because everything is loaded. Since everything is loaded and stored in the main memory, we do require the memory to be drawn all the time for every now and then. Okay, let us say that this is the current instruction that is being executed. Okay, that is this is the 23rd instruction. Okay, and the program counter is 24. Okay, the 23rd instruction is, let us say, ISZ, increment and skip if 0, 240. Okay, what is ISZ? Increment and skip if 0. This instruction stands for, we're going to increment and skip if 0. What? There is an address. You know that this is the instruction in which there are two parts. One is the opcode and the address of the operand. You people knew already about it. This is opcode and this is the address part of the operand. Now, what to be incremented? First of all, when we execute ISZ instruction, we will go to the respective location of the operand. How to, what is the address of the operand? Address of the operand is specified within the instruction itself. Okay, so in this case, we go to the address which is specified in the instruction, go to 240, in which there is an operand. Okay, the operand value is equal to 50. Okay, now we will get 50 into the CPU. We will get 50 into the CPU. We will send this 50 into ALU. In ALU, we are going to increment 50. Okay, so we will perform increment operation. What is incrementing? The content will get incremented. Then 50 will become 51. Okay, did I make it myself clear? That is, we are going to increment the operand which is available in the address that is present in the instruction. So we'll go to the operand's address and we'll collect the operand. We will increment the operand within the CPU. Of course, every time when we perform an arithmetic operation, that arithmetic operation will have to be performed only within the CPU. Okay. Now, after performing, we are going to compare this operand with 0. If the operand is 0, then we are going to skip the next instruction. The 24th instruction will get skipped. Once again, increment skip if 0. Increment skip if 0 stands for, the address part of the instruction will give you an address of an operand. Going to the address of the operand, we are going to collect this operand. After collecting this operand, we will perform incrementing operation. After incrementing, if the operand turns out to be a 0, then we are going to skip the next instruction. 24th instruction will not get executed. Rather, 25 will get executed. Did you understand, Mr. Lokesh? Did you understand this? That is, incremented skip if 0 is, we are going to increment the operand. After incrementing, if the operand is equal to 0, then the next instruction will get skipped. Otherwise, next instruction won't get skipped. In our case, operand value did not become 0 because 50 plus 1 is equal to 51 but not 0. So that the next instruction will not get skipped. Okay, this is all about ISZ. Did I make it myself clear? Good. Now, these are all what we call the memory reference instructions. There are a total of 7 instructions. If you remember, our opcode is equal to, our opcode is of 3 digits. Total instruction is of 16 digits. Total instruction is of 16 digits, in which the first digit is mode, you remember, Lokesh, and the next this is 1, next 3 digits are opcode, and then the least significant 12 digits are nothing but the address of the operand. You remember, Mr. Lokesh? If you say yes, then I will go to the next step. This is our instruction format. This is our instruction. No, my question is, you remember this instruction? In fact, we are designing a processor. In our processor, we designed the few registers in which there is an instruction register. The size of the instruction register is equal to 16. The way the instruction register has been divided is into three fields. The first field is a mode field, second field is an opcode field, and the third field is an address part of the operand. Right? Now, the opcode is 3 digits. Opcode is 3 digits. By using 3 digits, I can have 2 power 3 combinations which are equal to 8. Right? Did you get it? Now, 8 meaning from 000 to 111. Yes or no? Now, if you could remember, if you could stay focused, the total memory reference instructions are equal to just 7, which means that from 000 to 110, from 000 to 110 are given to memory reference instructions. Okay, but 111 combination, a combination of 111 hasn't been used for memory reference instruction. It is not a memory reference instruction. Then what it is? If 111 is not given to the memory reference instruction, then what it is? Then 111 could be either register reference or IO instruction, right? I explained you guys in my previous lecture. So how to differentiate in between register reference and the IO instruction? Definitely we will use the mode digit. If it is not a memory reference instruction, then there won't be any address. There won't be any addressing mode. Okay, these two fields will be free. We can use these two fields for different purposes. Once again, if it is not a memory reference instruction, we don't require an address, because only for memory reference instruction we do require a memory address, because the operands will be available in the main memory. If you want to access the main memory, we do require a memory address. Okay, if there is an address, there will be a corresponding addressing mode. If there is no address, there won't be any addressing mode. So what we do here is, we are going to use this mode field to differentiate in between register reference and the IO instruction. When the opcode is equal to 111, then it will be either a register reference or IO instruction. But what it is, just look at the mode. If the mode digit is equal to a 0 followed by 111, then it will be a register reference instruction. If the mode digit is equal to 1 followed by 111, then it is an IO instruction. You got this point? Okay. Of course, you definitely you do. Okay. This is as simple as this. Now, let us understand all these register reference and IO instructions. I use a PPT for that. Okay. Yeah. as you have seen this, and add load store BUN BSA ISZ. Next, this classification is register reference instruction. Okay, this part next to this will represent the hexadecimal code of the instruction. You know that 0111 is for register reference instruction, right? Did you understand, Lokeshwara? What is this combination? 0111. Of course, 0111 will tell you that the instruction is a register reference instruction. You're getting it. I told you that in order to differentiate in between register reference instruction and the IO instruction, we will use the first digit. If the first digit is equal to a 0 followed by the opcode 111, then this instruction is nothing but a register reference instruction. Okay. Now, this is going to tell you only that this is a register reference instruction. But where is the instruction? In order to design the instruction, what we do is we will use the least significant 12 digits. If you remember, earlier we used these 12 digits. We use these 12 digits for address in the memory reference instruction. In the memory reference instruction, least significant these 12 digits will represent a memory address. But now we don't need a memory address because it is not a memory reference instruction. If we don't need an address, all these bits will be free so that we can use this for some other purpose. What we'll do is, anyhow 0111 is only giving us the type of the instruction, rather format of the instruction that this does belong to register reference instruction. We'll use this for designing the instruction itself, the opcode itself. So what I'll do is, if you can understand this pattern, for every instruction I'm using a unique code. There are 12 digits. Okay, I'm flipping each digit for each and every instruction. For the first instruction, I use 1 in the first position. For the second instruction, I use 1 in the second position, third position. Did you understand this? Okay, for an example, the first instruction is CLA. What is CLA? I'll explain you about this instruction. First instruction is CLA. 0111 is common. Now, this I need to give an opcode for this. Opcode, in order to design the opcode, what I'll do is I will flip 1 digit each for every instruction. Okay. For CLA, in the 12 digits, I will put 1 in the most significant digit. I put 1 here. For CLE, I'll put 1 in the second position. For CMA, I'll put 1 in the third position. Is it making some sense? Okay. So, likewise, I am going to design all these instructions. So, each of these combination will represent one of the instructions. For an example, 10000 0000 preceded by 0111 will represent CLA. Okay. For this, hexadecimal combination will be 7800. 0111 is equal to 7, 1000 is equal to 8, 0000 is equal to 0, and 0000 is equal to 0. Okay. Now, CLA is 0111, 0100. 000 is equal to 400. Likewise. So, each and every instruction will have its unique combination. 7 is common because the first 4 digits will not change for any instruction for register reference. Okay. In the hexa, 0111 is equal to 7. Okay. So now, let us discuss only the significance of the instructions, the purpose of each and every instruction. CLA stands for clear the accumulator. What do you mean by CLA? When an instruction CLA gets executed, the contents of the accumulator will get cleared. The contents of the accumulator will get cleared. Regardless of the contents prior to this instruction execution, the contents will be flushed off to 0 when you execute CLA. Okay. What is CLA? There is an additional digit to accumulator, which is called extended accumulator. You came to know about it in one of my previous sessions. The accumulator size is 16 digits. Remember, the size of the accumulator register is 16 digits. right? Size of the accumulator digit is size of the accumulator is 16 digits. But when we perform any addition or subtraction or multiplication, we can't have a guarantee that the contents of the accumulator will still be equal to or less than 16 digits. There may be a 17 digit, yes or no? So at that time, in order to accommodate that carry, we will have an additional digit which is called an extended accumulator. We employed an extended accumulator in order to accommodate the carry. In order to accommodate the carry. Just a minute. In order to accommodate the carry. Okay. So when you execute CLE instruction, good. When you execute CLE instruction, what will happen? Contents of the extended accumulator will get cleared, regardless of the contents before the execution of CLE. The contents of extended accumulator will get flushed out, will be equal to 0 after executing this. CMA. What is CMA? CMA stands for complementing accumulator. What is complementing? Tell me, Lokesh, answer this. What do you mean by complementing accumulator? That's my question. What do you mean by complementing? Are ones to zeros, zeros to ones, right? Complementing is just nothing but the ones will be turned out to be a 0, zeros will be turned out to be ones. That is what all about complementing. Yes or no? You know complementing? You know one's complement and two's complement? Do you or you don't? First of all, am I audible? You want to answer? 0 become 1 and vice versa. Yes, absolutely. Okay, so complement accumulator, when instruction CMA gets executed, contents of the accumulator will get complemented. When CME gets executed, contents of the extended accumulator will get complemented. Okay, that's it. That's it. Okay, CIR, CIL. What is CIR? CIR stands for circular shift right. CIL stands for circular shift left. Okay, what is circular shift? You know what is circular shift? Circular shift means the contents of the accumulator will get rotated. Okay, you know shifting. Do you know or you don't? For an example, I will write it here. There is the contents will be, let us say, 0, 1, 0, 1. Okay, let us say it's my accumulator is just 4 digits. What will happen after rotating? Right rotating meaning each and every digit will occupy the next the right subsequent bit position. This 0 will come here, this 1 will come here, this 0 will come here, this 1 will get rotated and will occupy the first position. So after right rotating, the contents will get transformed into 1 0 1 0 0 1 0 1 will get transformed into 1 0 1 0, because each and every digit will occupy the next right subsequent bit position. Okay, this is what all about circular shift right. Okay, and then circular shift left. Circular shift left stands for just in contrast to CIR. Here in the previous case we are shifting right. Now in this case we are going to shift left. So what will happen is this 1 will come here, this 0 will come here, this 1 will come here, this 0 will occupy the least significant bit position. Okay, which means that 0 1 0 1 will become 1 0 1 0 anyhow. Okay, so that is all about circular shift right and circular shift left. Okay, and another thing is increment. What is incrementing? Incrementing is simply incrementing. But what to be incremented? Here, for everything, there is only one operand here. For all the register reference instruction, the default operand will always be the accumulator, either CIR, CIL. or CLA, CLE, CMA, CMA. For everything, only the operand, one and only the operand on which the operation will get performed is accumulator. Simple. I hope you got my point. For every register reference instructions, needless to say, the obvious operand will always be accumulator. Got me? Yeah. So incrementing meaning the contents of accumulator will get incremented after executing this instruction. SPA. Okay. What is SPA? As you can see here, skip the next instruction if accumulator is positive. I will demonstrate this instruction by taking an example. Okay. Let me draw. Again, main memory. Let us say the current instruction is 46th instruction. The 46th instruction is what is that? SPA. This instruction is SPA. Skip the accumulator, skip the next instruction if the accumulator is positive. Okay, SPA. Skip the next instruction if the accumulator is positive. For that, what we need to see is, we will check the contents of the accumulator. If the contents of the accumulator is positive, then the next instruction will get skipped. Okay, rather, the next subsequent instruction will get executed. We are going to skip the next instruction. 47 will get skipped. Rather, 48 will get executed. This is the significance of SPA. But stay focused. Okay. For that, there is something more to add to this point. You know accumulator register. Accumulator is a 16-bit register in which the most significant digit, that is the 15th digit, 0 to 15. The most significant digit is what you call a sign digit. If it is 0, it is positive. Rather, if it is 1, it is a negative. Right? In order to identify the contents of the accumulator, either those are positive or negative, we need to check the most significant digit. Checking one digit in the accumulator will always be very difficult. Rather, what we do is, rather than coming to the accumulator and checking it, what we do is, we will directly check the flag register. If you remember, there is a flag register in the system which shows the status of the accumulator. I explained you already. Okay, the flag register will show the status of the program. What is the status of the program? Every time when an operation is performed due to the execution of an instruction, flag register will get updated. I explained you about several flags, okay, including the important flags such as Z, S, C, V. There is a Z flag, there is a sign flag, there is a C flag, there is a V flag. Let us say this is my AL. This is my AL. Now one instruction is getting executed. During the execution of the instruction, the ALU is going to perform one arithmetic or logical operation. Okay. When ALU performs an operation, finally it has to send the output. The output of the ALU will get transferred to the accumulator. Many times we learned about it. Okay, in any architecture, the output of the ALU will get transferred directly to the accumulator. Okay, at the same time, the output of the ALU will also update this flag register. Okay, now if the output of the ALU is a 0 flag will be equal to 1. If the output of the ALU is negative, then sign flag will be 1. Otherwise, if it is positive, it will be equal to 0. If the output of the ALU has a carry, then carry flag will be equal to 1. If the output of the ALU has an overflow, then overflow flag will be equal to 1. The overflow, what do you mean by overflow? Overflow meaning accidentally sign is getting reversed. Okay, sometimes what will happen is sign will unnecessarily get reversed. Okay, during the execution of some instruction. For an example, when you add two positive numbers, the result must be a positive number. There is no way that we can get a negative result when we add two positive numbers. For an example, I am adding 0 triple 1, 0 triple 1, which means that we are adding plus 7 to plus 7. Let us say the size of the register is just 4 digits. Okay, but as the most significant digits are equal to 1, there will be a carry that will be produced and it will occupy the sign digit. So at that time, sign will get reversed. You understanding, Lokesh? This is very simple. Of course, plus 7 should be equal to plus 14. But here, in our case, plus 7 as the register size is limited is actually reversing the sign digit. Did you get it? But actually, it has to be a carry that should go to the carry digit. But rather, it is reversing the sign digit. Did you understand, Lokesh? Yeah, good. Now, whenever overflow digit is equal to 1, it shows an important status of the output of the instruction from the ALU. Okay, the ALU computed, and due to the limitation of the size of the register, the actual sign has been reversed. Okay, so whenever overflow digit is equal to 1, the sign has to be reversed. Did you get it? The sign has been reversed. So what we do is whenever overflow digit is equal to 1, whenever overflow digit is equal to 1, that means that there is a carry. But due to the size of the limitation of the size, it is occupying most significant digit. So whenever there is overflow, this C must be equal to 1. This sign must be reversed here. This is how we are going to deal with sign reversal. I'm not going to talk much about this because this is the simplest phenomenon and I've already explained you in one of the previous sessions. Okay, fine. Anyhow, that is the difference between carry and overflow. Carry is a phenomena that is whenever two equivalent numbers are getting added and the result is an additional digit, then we are in a situation called carry. But whenever a sign digit has been reversed unnecessarily due to the limitation of the size of the register, then we are in a situation called overflow. Whenever overflow is equal to 1, then what we do is we will reverse the sign digit and set the carry digit. This is how we are going to deal with the sign reversal. Okay, fine. So what is SPA? Skip the next instruction if the accumulator is positive. Skip the next instruction if the accumulator is positive. Okay, we will go and observe sign digit here. If the sign digit is equal to 1 means accumulator is negative. Okay, if the sign digit is equal to 0, then the accumulator is positive. If the sign digit is equal to 0, we are going to skip the next instruction. Rather, we are going to execute the 40th instruction. Otherwise, we will execute the next instruction. Similarly, SNA. If the accumulator is negative, next instruction will be skipped. Otherwise, next instruction won't get skipped. Similarly, SZA. Skip if accumulator is 0. We will observe the 0 flag. If the 0 flag is set to 1, that means that the contents of the accumulator are equal to 0. So what we do is we are going to skip the next instruction. Otherwise, we are not going to skip the next instruction. Okay, and SZE. Finally, we have one more instruction called SZE. What is SZE? Okay, SZE. SZE stands for skip the extended accumulator is equal to 0. Skip the next instruction if the extended accumulator is equal to 0. Okay, so what is extended accumulator? You know that the additional digit and carry both are equal to 1. We are going to observe carry digit. Whenever carry digit is equal to 1, then we don't skip the next instruction. But whenever carry digit is equal to a 0, that means that extended accumulator is equal to 0, then we will skip the next instruction. Did you understand this? Why carry and extended accumulator both are equal? Of course, obviously, what is extended accumulator? Extended accumulator requires to be filled whenever there is carry only, right? Yes or no? So obviously extended accumulator and carry both are equal to 1. Okay, so the next instruction is halt. Okay, write it down somewhere. I'm going to explain you some important thing about halt instruction. Okay, what is halt instruction? Yeah, let us say this is one instruction. The address of this instruction is 21. Okay, yes or no? If this instruction is getting executed, what will be the program counter value? Lokesh Parak, what will be the program counter value? The current instruction is 21. CPU is executing 21st instruction. This is current instruction. Yeah. Current instruction is 21. For the current, if the current instruction is 21, for 21, what will be the program counter value? Yes, this is 22. Program counter value is equal to 22. Yeah, this is always correct. When 21st instruction is getting executed, the program counter value will be equal to 22. When 22nd instruction is getting executed, the program counter value will be equal to 23, and so on. That's it. This is applicable for all the other instructions except halt instruction. Okay, except halt instruction, for any other instruction, when those are executed, the program counter value will be the address of the next instruction, obviously. But let us say in 21 there is a halt instruction. Okay, if 21st instruction is a halt instruction, then the program counter value will not be 22. Rather, program counter will also be equal to 21. That's it. Okay. For any other instruction, when that is executed, the program counter value is the address part of the next instruction. This is the address of the next instruction, except halt instruction. Only for halt instruction, the current instruction address and both program counters value are exactly equal. Okay, program counter value will not be updated for halt instruction. If you digest this, we will enter into the details why for halt instruction program counter value will not get updated. If you could understand this, I will get into the details. We will see why it is. Okay, right? But it is thumb rule. For every other instruction, program counter value is the address part of the next instruction except halt instruction. It is applicable to every other instruction, but not for halt instruction. Got me? If you can understand this, I am going to give you the complete detail about this halt instruction. I am going to take you to the extent that you can understand why why for the halt instruction program counter value will never get updated. You there? Am I audible? I think for me, it's been stuck. Yeah, you're right, but it is used to switch the interrupt service. Fine, but you do not think too much. Using interrupts to understand this concept will be somewhat complex. Rather, I'll simplify it. Yeah, good. Now stay focused here. Um, Let us say I do have memory. Okay, this is my main memory. I will draw one more. I will give you an overview of memory from the perspective of programs. In the main memory, there are n number of programs. Okay, these are programs, these are not instructions. Now I am giving you the view of the main memory in terms of the programs. This is program 1, this is program 2, this is program 3, program 4, and finally we do have something called a program n here. Now, now the system has been started. Let us say the computer system has been switched on. Okay, and the main memory has been loaded with the number of programs that are needed to be executed currently. Now could you please tell me, let us say I'll give you also another example that CPU decided to execute program 4 right now. Okay, program 4 is being executed. Okay, let us say program 4, the address range is from 300 to 400. Program 4's address range is from 300 to 400. Any instruction in between 300 to 400 falls under programs 4. Okay, if you want to execute program 4, you need to execute all the instruction right from 300 to 400 inclusive. Okay, now I do have a question. Forget about halt instruction. When 301 is getting executed, obviously the program counter value is 302, right? When 302 is getting executed, obviously the program counter value will be equal to 303, and hence so on. Yes or no? But now I do have a question. Answer me very carefully. After executing program 4, which program will be executed by the CPU? Answer carefully. After executing program 4, which program will get executed by the CPU? I am waiting. After, my question is very simple. After executing program 4, which program will get executed? Simply you fall in the trap that I have created for you, that I have ditched for you. There is no way, we can't tell which program is going to get executed. The instructions that are available within the program will get executed continuously, one by one, contiguously. But the programs will not get executed contiguously in the main memory. This is the fundamental rule that you need to understand. There is a scheduler. Let me take the help of the operating system in this case. There has been a scheduler. There is a scheduler. Scheduler will decide. There are several factors will be considered by the scheduler. Maybe a shortest job first or longest job, and like there are several scheduling criteria. Okay. Let us say I'm using the shortest job for scheduler. Shortest job for scheduler is going to pick up the shortest job among the jobs that are available in the main memory after executing the current program. Did you get it? There is a scheduler that is going to decide which program is going to get executed next. Okay, and there is no way I can tell you that after this program, next program will definitely be executed. There is no rule, and I don't know. Neither you nor me knew about the next program that is going to get executed after the current program gets executed. This is a thumb rule. There is a scheduler. The scheduler will decide the fate of the program that is going to be executed next by using a scheduling criteria. It could be shortest job first, or the shortest remaining time first, or longest job, or longest remaining time first, or round robin, or whatever. Okay. So here, let us say the current instruction is 400, which is the final instruction of the current program. Did you get it? So what generally had been done in the previous days of computing was the programs used to get separated by using a halt instruction. Okay, after finishing the current program, there had been an instruction such as halt used in order to separate this program from the next program. So let us say I reached the far end of this program, that is the 400th instruction, meaning in 399 itself the program has been finished. The final instruction has been available in 399th instruction. So obviously the final instruction will be halt. What is halt? Halt meaning the system will be halted till the scheduler decides the next program to execute. That is the reason why when halt instruction gets executed, program counter will not get updated. Rather, program counter will repeatedly be updated to the current instruction's address only. Okay, I'll tell you once again. Okay, now there is a program. Now currently P4 is being executed. P4 is in between 200th instruction to 300 instruction. Okay, for every instruction the program counter value will get updated, but the final instruction 300, program counter value should not be updated to 301, right? Did you get it? If the program counter value gets updated to 301, we are violating one important rule such that the program counter value should not be updated to the next program's address. The program counter is the current program counters, current program's counter. Program counter cannot count the first instruction of the next program. So, did you understand? Program counter value should be only for the current program. The program counter should not be updated to the next program at all. So, what we do is the final instruction will be written. It's just nothing but a halt instruction. Okay, when halt instruction gets executed, program counter will be repeatedly updated to 300. What is halt? Halt will be realized by using one instruction called branch unconditionally to the same location, BUN 300. Okay, what is branch instruction? Whenever, what is branch? Branch unconditionally meaning we'll jump to 300. During the branch instruction, we will branch to the address part of the instruction. That is, here halt instruction will be realized by implementing a jump instruction to the same location. That's it. Okay. You might also have a doubt that always program counter needed to be executed, needed to be updated. Then how halt instruction can stop updating the program counter to the next instruction rather than to the current instruction? The answer is simply this one. That is, halt instruction will be implemented by using a jump to the current instruction's address. What is BUN? Jump to the address 300. What is 300? Current instruction's address. Again it gets executed. BUN 300. Again it jumps to the same instruction. I hope you got it. Did you or not? Okay. So this is all about halt instruction. For halt instruction, program counter value will never get updated. This is the thing. Did you get it, Lokesh? Yeah. No. Halt meaning halt instruction. There is no such instruction called halt instruction. Halt is a status of the computer system. In order to implement, in order to present a halting situation, what we do is we will perform a jump repeatedly to the same instruction. So computer system is said to be in the halt state, right? There is no instruction such as halt instruction. There is a state such as halt state. Okay, so how to have the computer system halted? I should stop streaming the instructions. I should stop the stream of the instructions from execution. How can I stop it? There has to be a point at which the computer system has to be halted. That point is an instruction. That instruction, for that I do use a jump instruction, jump to the same location again and again and again and again. When it happens, the control will not go to the next location. If the control goes to the next location, then we will come out of the halt state. Next sequence of the instructions will get started. Next sequence of the instruction will start its execution. When we want to halt, we will use jump to the same location phenomena. I hope you got it. Okay, so this is all about halt instruction. So you remember this. So in most of the previous questions, there had been a mention of the halt instruction. Most of the guys went wrong. This is an important phenomena. Most of the people, they didn't know. Even the computer architecture, major people who teach us computer architecture don't know about this. Okay, so consider to be you guys are very lucky to understand this, because you don't know from which source you're going to have the important details of a subject, a topic. So write it down this, and better you explain it to some guy who is absent to my class, so that you're going to enhance your computer architecture skills. Okay, that's it. That is halt instruction. After which I'm going to take you to the next set of instruction. Those are the IO instructions. IO instructions, first to 4 bits are equal to 1111, because 111 is an opcode combination for both register reference and IO instructions. We don't have to differentiate. We use the first digit. If the first digit is equal to a 0, then it was a register reference instruction, but now it is an IO instruction. You got my point? So now 1111 followed by, I will use the least significant 12 digits to compose instruction. 1111 1000 0000 0000. It is the first instruction, which is nothing but INP. If you convert this to hexa, you will get F800. 1111 is F, 1000 is 8, 0000 is 0, 0000 is 0. Next combination is out, that is F1 will not change, rather 0100 0000 0000. Likewise, every instruction will flip one digit each in the least significant 12 digit to get composed. Okay, so the first instruction is INP. INP, when INP gets executed, a character will be accepted from the input device. Okay, a character will be transferred from input device to the accumulator. When you press the character, the character will get transferred to the input register. Okay, but where that character should be transferred? The character should be transferred to accumulator. Actually, you know that accumulator is the main register. I will talk more about this. Finally, the character has to be transferred to the accumulator. When you press the key, immediately the character will get transferred to the input register, but input register is not the final destination. So what we do is, we are going to execute one instruction called INP. When INP gets executed, then a character will get transferred from input register to the accumulator. OUT. When OUT gets executed, a character will get transferred from accumulator to output register. From accumulator to output register. Okay. SKI. There are two flags in the computer system. One is input flag, one more is output flag. More about these flags, I will explain you, I will teach you in interrupts. But at this stage, you understand that there are two flags, input flag and output flag. Input flag will be raised whenever input device trying to communicate with the computer system. Output flags will be raised whenever output device is trying to communicate with the computer system. So when one of these instruction gets executed, corresponding flag will get skipped. If SKI gets executed, input flag, no matter what, input flag, the the value of the input flag, whatever it is, computer ignores. SKO, value of the output flag, whatever it is, the computer system simply ignores. ION, when this gets executed, the interrupt facility for that program will be switched on. When IOF gets executed in any program, interrupt facility for that respective program will get switched on. Okay. So this is all about the various different instructions which are classified into three different categories. The first one is memory reference, second one is register reference, third one is IO instructions. So next week we will take up another important topic. Till then, take a long 7-day break. Okay, good night. Same day, same time, we're going to meet next week.